To continue our review of algebra before we get started with the calculus portion of the course, let's go ahead and look at representing functions. Now, first of all, functions can look very different. We've already talked a little bit about what they look like, but we specifically want to talk about two types of functions. The first one is a polynomial function. The word polynomial, poly means many, so this is many terms basically. Now, a polynomial function has a form ax to the n, bx to the n minus 1, and this pattern would continue down. Now, n is some sort of an integer, so the thing that you might see here is something like 3x to the 5th plus 2/3 x to the 4th plus 9x cubed minus 1/3 x squared plus 2x plus 1, let's say. As an example, this would be a polynomial, definitely many terms here. Now, when we look at this expression, there's a couple things that we see. First of all, the powers are integer values. They're not negative, they're positive integer values. They're not fractions. The coefficients in front can be fractions, but the powers themselves are just integer values. Now, there's a neat characteristic about a graph of a polynomial function, and that is that it's a smooth, continuous curve. So some graphs that would be polynomials might be something like these. Could just be a straight line as well. Could be a nice shape like a parabola. So smooth and continuous. There's no jumps or there's no gaps. Now, if we talk about a polynomial function, one of the characteristics that we like to refer to is the domain. Now remember, the domain is the horizontal axis, meaning what values are covered on the horizontal axis. Well, in these particular cases, we can see that all the values of x are covered on this horizontal axis. This arrow on the end indicates this goes on forever in this direction. Now, a lot of the graphs created by technology don't have the arrow on the end, and that's implied to go on forever unless stated otherwise. This one, if we look at all the x values that are covered, you can see that there's no gap or there's no spot where I could not plug in an x, and the same here. So the domain is all real numbers. And there's a lot of different ways that we can represent this. One way that we could look at this is we could say negative infinity to infinity. Now, we don't have equality at infinity or negative infinity, so that's why I just have a less than sign and not a less than or equal to sign. Another way we could represent this is negative infinity to positive infinity using interval notation. So this is interval notation. This is set builder notation. So that's the domain of a rational expression. Now there's another, domain of a polynomial expression. Let's go ahead and look at the rational expression next. Now, a rational expression is basically a fraction. It has a numerator and a denominator. And it looks like a over b, but of course the denominator can never be equal to 0. If the denominator could equal 0, then we'd have an undefined fraction. So what ends up happening with a rational function is I want to talk about that domain part again. So the domain of a rational expression can be anything except what makes that denominator equal 0. So for a rational expression, the denominator cannot equal 0. So that's one of the things that we need to keep track of when we're looking at a rational expression. And of course, it's going to matter what that denominator is. So if we looked at a specific example, we could have something like 2 over x minus 4. And so to find the domain here, what we could do is we could say, well, I can have anything except when that denominator x minus 4 equals 0. So the denominator cannot equal 0, so we'd go ahead and add 4 to both sides. So I get x cannot equal 4. Okay? So x cannot equal 4 would be the restriction. So that's one way to talk about the domain. I could say, well, x can be anything except 4. Another way we could talk about this is we could say, well, we could have negative infinity to 4 union from 4 to infinity. Now this is interval notation. Now remember, what this notation means is I can have any number from negative infinity up to 4. This is a parenthesis, so it means I get very, very close to 4, but I never reach 4. And then I start up again right after 4. That's why this is a parenthesis, and it goes on toward positive infinity. So that would be another way to represent this as well. So basically all real numbers except where the denominator cannot equal 0. A linear function is another function that we work with quite a bit. And of course, in order to work with a linear function, a graph is always helpful. So let's go ahead and look at a linear function. Now the graph that we're going to work with in this particular case, I'll just look at 2 points on the graph. So let's look at the point, let's say 2, 4. And then our other point, let's say, is -3, -5. Okay, so we'll go ahead and connect these. Now this is not extremely accurate. It's not really to scale. So it looks like it crosses near the origin, but I'm not going to depend on that because if I move my tick marks around, that could change. So let's write what these points are. This is the point 2, 4. And this was the point -3, -5. Now what I want to do is I want to find the linear function that corresponds to this. Now when I talk about the word function, we might want to start thinking about what functional notation is. So in your homework sets, what you'll be given is f of x equals, and then you'll be given this big blank to fill in right here. So this is that functional notation that we're looking for. This is the same as replacing it with y. So this is another way to look at the same problem. So f of x is interchangeable with y. Now to find the equation of a line, there's a lot of different ways that we can do this, but one thing we have to do is to be able to find that slope first. So the slope, if you'll recall, is the change in the y values over the change in the x values. Y is my vertical axis, x is my horizontal axis. And the important thing to look at here is to make sure you're moving in the same direction. So a lot of people write this formula y2 minus y1 over x2 minus x1. So that could be another way you could look at this. Arbitrarily, I'm going to choose this to be x1 and y1. And this could be x2 and y2. Now if you chose opposite, we'd get the same answer in the end. So it doesn't matter which point we use as x1, y1. So in our case, y2 is -5 minus y1, which would be 4. x2 is -3 minus x1, which is 2. So I have -9 over -5. The negative divided by negative is a positive, so I'm left with 9/5 for my slope. So that's an important piece of information. Now there's several different things that we can do from here to find the equation of a line. I'm going to look at the equation y equal mx plus b. And if you want to use the point slope equation of the line, you can use that as well. And I'm going to plug in my slope that we just found. And I'm going to choose one of these points. It doesn't matter which point we choose, I'll get the same answer in the end. I'm just going to choose the -3, -5. Okay, if you wanted to choose the 2, 4, that's okay, we'll get the same answer in the end. So what I'm going to do is I'm going to plug in -5 in here. My slope was 9/5. My x value is -3 plus b. So my goal here is to solve for b. So I have -5 equals -27/5 plus b. And then of course to solve for b, I would add the 27/5 across. So I have 27/5 minus 5, which is 25/5. So this is 5. So that came from right here. So I added the 27/5 across and I subtracted 5, which is the same as 25 over 5. So I get b equals 27 minus 5 is 2/5. So now I have my slope from right here, and I have my y-intercept from right here from my y equals mx plus b form, and I can plug these both into that idea of y equal mx plus b, but I'm not going to be plugging in a particular value for y and x this time. So m was slope, that's my 9/5, x plus b, which is 2/5. And so this is my slope-intercept form, this is my y-intercept, and of course 9/5 is my slope. I'm sure you've done a lot of these when you're working through algebra, so that's just a little bit of a review. Another interesting function that we like to talk about quite a bit is a piecewise function, and you'll run into piecewise functions a lot in calculus, especially when you're working with limits. So let's go ahead and look at a piecewise function. And again, the best thing to do for a piecewise function is to go ahead and look at a graph. And then a lot of times from the graph, you'll be trying to find the equation that matches it, or sometimes you'll be given the function and asked to work backward. So for this example, I'm just going to give you the function, and then we'll create the graph. So I have 2x minus 4, and this is only defined over a particular domain. So this is only for x values that are less than -1. It could be equal to a -5. And this is only defined for x values between -1 and 2. Notice I have equality at -1 and 2. And then I have -x for x greater than 2. Okay, so as I get started here, I'm going to notice a few characteristics. First of all, this is a positive sloping line. So this is a graph that's going to look something like this. This is just a constant. This is y equal -5. So this is just a constant graph. Now this is a line that has a negative slope. So it's going to look something like this. And I'll remove this arrow just so it's not confusing. So this first one has a slope of 2 and a y-intercept of -4. This is a horizontal line through -5. Y equal -5, it's horizontal. So this one, my slope was -1. It's an implied 1 out front and it's negated. And my y-intercept equals 0 because there's a +0 here. Now I'm going to try and piece together all this information to create a nice little graph. Now as usual, scale matters here. So your graph may look a little bit different based on how we have our tick marks laid out and all that type of thing. But I will say that it should have the same general shape. Now you can graph these on your calculators as well if you want to Google, how to graph a piecewise function on your TI-84 or whichever calculator you have. But it's important that you be able to work with these by hand because you won't have access to a calculator on your exams. You will have a note card, however. So let's go ahead and start with this -5. I think that's the easiest part. So it says if I plug in a -1, I'll get a -5 back out. 1, 2, 3, 4, 5. So that's this point. I could plug in a 0, that's in this interval as well, and I'd get a -5 back out. And this goes all the way up to 1 and then to 2. Now because I have equal signs at both of those endpoints on the domain, these are filled points. Okay, so this is -5. This is the blue line. Okay, let's go ahead and look at another piece to this. Let's go ahead and look at this -x. And you could do these in any order. This says for x greater than 2. Well, I'm going to plug in a 2. I know this says greater than, but I'm going to plug in a 2. And if I plug in a 2, I get a -2 back out. But it's a hollow point because I don't have equality at 2. Now I know that I'm only looking at values that are greater than, so I'm not going to move in this direction to find the y-intercept. I have to move in the positive direction. So let's go ahead and then plug in a 3. So if I plug in a 3, I get a -3 back out. So 3, -3. So I'm moving in the positive direction for my x values and my y values are moving down. So that's what this line looks like, and it goes on forever, so I could have an arrow on the end. So this is my orange line, and again, negative sloping line. Okay, last piece here, let's go ahead and look at our first function, and this is for x less than -1. I'm going to do the same thing and plug in a -1. 2 times -1 is -2. -2 minus 4 is -6. So -1, 1, 2, 3, 4, 5, 6. Now that's a hollow point because I don't have an equal sign here. Okay, so let's go ahead and plug in something like a -2. If I plug in a -2, I have -2 times 2 is -4. -4 minus 4 is -8. 3, 4, 5, 6, 7. We need one more tick mark down here. So if I include that, it would be this point. That would be this part of my line. So this is the piecewise function represented by this f of x up top. Now, a couple things I want you to note. It is a function because it passes the vertical line test, and it is important to find out where these points are hollow and where they're filled. So when you're working with these graphs, again, look at them piece by piece and kind of analyze what's going on with each piece. How should each piece look? And then just focus on each individual piece instead of the overall graph. And these are pretty straightforward to work with. So knowing some of those characteristics is going to be pretty important. Now, everything we looked at so far has had to do with x's and y's, but that doesn't always have to be the case. One of the problems that you could run across in your homework is working with temperature. So we're going to be working with the Fahrenheit scale and the Celsius scale. And so instead of x's and y's, we'll have c's and f's. So for this example, let's go ahead and talk about Celsius and Fahrenheit. So let's go ahead and make a little table. There's a couple of pieces of information here that most people are aware of. First of all, when I'm 0 degrees Celsius, that's when water freezes. That's 32 degrees Fahrenheit. We also know that Celsius at 100 means water is freezing. Water not freezes, but water boils, which is equal to 212 degrees Fahrenheit. So this is some standard information that a lot of people know. Now, you can take this information however you want. If you want to use this on the horizontal and this on the vertical, it doesn't matter. So let's go ahead and try and sketch this out a bit. We're going to focus on the first quadrant here, so I won't put up all the quadrants. I'm going to put Celsius on my horizontal axis and Fahrenheit on my vertical axis. And it's important that we write which is which here, because we'll need to know which is the independent and the dependent variable. So we could graph the point on 0, 32. So let's say here's the point 0, 32. Now we also need the point 100, 212. And I know that this is not exactly to scale, but it gives us a good idea of where to get started. So this is the general shape of our graph. Now what I want to do is come up with an equation that allows us to, given Celsius, predict Fahrenheit. So if I input Celsius, I'll get Fahrenheit back out. So what the question here is that you might run across in my math lab is they're saying find a formula that looks like this. They're not having the F out front, they have C equals. So we could set this up one of a couple ways. I could have switched these axes around, but we'll get the same answer in the end if you started different. So same problem as we did last time. I have 2 points. So the first thing I need to do is to go ahead and find slope. So again, slope we said was the change in y over the change in x, but I don't have x's and y's here. Fahrenheit has replaced my y-axis and Celsius has replaced my x-axis. So that would be Fahrenheit 1 minus Fahrenheit 2 over Celsius 1 minus Celsius 2. And again, it doesn't matter which point is which here. I'm just going to call this C1F1 and C2F2. And if you did F2 minus F1 over C2 minus C1, that's fine. It just doesn't end up mattering as long as you're consistent with the direction. So the change in my y values or my vertical values would be the 32 to 212, so 32 minus 212. And then I start with this point again over 0 minus 100. So 32 minus 212 will give us negative 180. And our denominator is negative 100. A negative divided by negative is a positive. So this would reduce to what, 18 over 10, which further reduces to 9/5. So there's my slope. So now I can choose a point. And I think the easier point to do here would be 0, 32. And my slope would be 9/5. Now in the last problem we did, I plugged it into the y equal mx plus b form. And we could do that again if we want. I'm just going to show you another way that we could do the same problem, just so you can kind of see a couple different approaches. So for this one, I'm going to use the equation y minus y1 equals m times x minus x1. Now remember, our y's are Fahrenheits. So this would be f minus f1 equals the slope times Celsius, because that's my x-axis, minus Celsius 1. Now F1 and F2 are right over here. Or sorry, F1 and C1 are right over here. My first value here was centigrade. Make sure I get these in the right spot. So this is C1, F1. So this is F minus 32 equals 9/5 times C minus 0. And so this is nice because we have that C minus 0 on the right hand side. So I have F minus 32 equals 9/5 C. Now if you remember, the original problem asked us to find out what C equals. So C equals is what I'm shooting for here. So I will need to solve for C. I want C by itself. Well, in order to clear this fraction, you can divide by 9/5, or another way to think about that is multiplying by the reciprocal of 9/5, which is 5/9. And of course, whatever you do to one side, you have to do to the other to keep that balance of our equations. So the 5 and the 9 cancel. And on the left-hand side, I'm left with this. I don't want to distribute it. And then I'll have C equal 5/9 times the quantity F minus 32. So I can derive that formula based on those 2 points that I have. So up here, this would be 5/9 times F minus 32. So that's how we can derive that temperature formula that we use a lot. Now there's another part to this question. This part would be, at what temperature are the readings equal? And if we look at our trend here, we see something kind of interesting. So if we look at these ordered pairs, if you notice, when we're at 100 and 212, that's 112 degrees difference. And here we are now, we're moving down, and now it's only a 32 degrees difference. So I'm thinking at some point, the degrees Celsius and the degrees Fahrenheit will be identical at a particular temperature below 0, because I see that trend happening. Well, how could we figure out what's going on with that? Well, there's a couple different ways. First of all, we could start with our equation. And I could say, well, you know what? Right now I have two variables. I have Celsius and Fahrenheit. But really what I want to know is when they're the same. So instead of saying what C equals and F equals, I'm going to say, you know what? At what temperature are they the same? So I'm going to replace both the Fahrenheit and the Celsius with just the variable T. And that's to represent the fact that at some point the two temperatures are the same. Now what I want to do is solve for T. So I'll distribute, I mean there's quite a few different ways that you could do this, I guess. You could distribute the 5/9 T, or probably a real quick way to go after this would be to multiply both sides through by 9/5. And the reason that might be nice is it clears my fraction right away without having to distribute. So I end up with 9/5 T equals T minus 32. Then I will subtract T from both sides because I'm trying to solve for T. So I end up with 9/5 T minus T equals negative 32. Well, I need to find a common denominator here in order to combine these. So this would be 9/5 T minus 5/5 T equals negative 32. 9/5 minus 5/5, 9 minus 5 would be 4/5 T equals negative 32, and then the last step is to clear that fraction again. Now there's a lot of different ways we could have done this, so if you had a different approach, that's great, but we'll end up with the same answer in the end either way. The 5's and the 4's cancel, so I'm left with T equal, let's see what we have here. 4 goes into negative 32, negative 8 times 5 is negative 40. So our answer here is negative 40 degrees. Now I think in my math lab, what they do is they say blank, and then they put in the word degrees over here. So you could just put in negative 40, and then the word degrees is taken care of. So basically this means negative 40 degrees Celsius is exactly the same temperature as negative 40 degrees Fahrenheit. It feels the same. The next function that we want to come up with, it will not be one that's provided to us, but one that we have to develop or derive on our own. So for this one, this is pretty typical idea, is to talk about a box. Now we're going to be using an algebraic approach to solving this problem. So this says we have a lidless box. And it's important that it's lidless because that's going to change how we look at the surface area because there is no lid on top. So lidless box, we have, to use our imagination a bit here, but they're telling us that we have a square base. And so if we have a square base, that means each of these dimensions is the same, and then we have some sort of a height. We're also given that the volume of this lidless box is 101 cubic feet. Okay? What I would like to know is I would like you to find a surface area function. So I would like you to find the surface area. Now we can't find the surface area unless we know some particular values here, so I'm trying to find the surface area function, meaning I'm trying to write something that represents the surface area in terms of x. And we'll talk about that in terms of x here in a minute. So if I start talking about surface area, I can see that I have on the bottom of this box, I have this bottom piece, and that surface area is x squared. I don't have a top that relates to it though because this is lidless. I also have this front piece, which would be base times height for the area of this piece, which would be xh. And I also have one of those in the back. So I have the one in the front and the one in the back. So I have the bottom and I have the front and the back, and now I need the two sides. Now the side, this piece right here, the area is x times h. And I have a right side and I have a left side. So again, this is the bottom, front, back, right side, left side. Now when we're working with this, we can definitely simplify this quite a bit by rewriting this as x squared plus 4 of these xh's. But remember, I wanted to write this in terms of s of x. So in terms of s of x, that means I need the h to go away. So I want to know, what does h equal? Well, we were given some other information. I was given that the volume was equal to 101 cubic feet. Well, the volume of this box is not affected by the fact that there's no lid on it. It will still hold the same amount, I just won't have a lid on top. So the volume of this box is x times h, base times width times height. So the volume is x squared h. So this is getting me somewhere because I need to know what h equals. So I could divide both sides through by x squared. And then from this information, I know that h is equal to 101 over x squared. So that means I can take that and plug that in right up here. So now this equation will be in terms of x. So I'll have x squared plus 4x, and then in place of that h, 101 over x squared. Now this can be simplified. So I have x squared plus 4 times 101 would be 404. And then x cancels into the x squared x times. So this is my formula. X squared plus 404 over x. And this is how you would derive it. Now this is a reasonable question to have on an exam. So again, make sure when you're working through these, you remember how to derive the surface area and the volume. Now I want to know next, this is my function that I have here. I would like to graph this. And we're going to use a graphing calculator for this. And then I also want to try and figure out the value that produces the minimum box with the minimum surface area. So what value of x produces that same volume that we're talking about with the minimum surface area? Now this is a good question because this has to do with packaging. So if I was packaging a product, I want to use the least surface area possible because it costs me less. And then if you're into environmental issues, you want to use the least packaging possible because you want to make sure that you have the least amount of waste going out into the environment. So whatever your graphing calculator looks like, let's go ahead and pull one up here that I have. We want to graph this. So the way we would graph this is we'd go y equal, and we'd put in our x squared. X is our key here. I'll clear this out and enter it again. x squared plus 404 divided by x. Now if you have that fraction key, remember it's alpha y equal, I would encourage you to use that. Let's go ahead and hit graph. And I think you're going to have to adjust your screen quite a bit. Make sure when you adjust your screen you can go to window and you can change your settings until you can kind of find a spot that works for you. In my math lab, a lot of times they give you suggestions on what to use for the scale. So this is a picture of what that function looks like. So let's go ahead and put that in our notes first. So again, we want to find the value of x that minimizes the surface area. I want to minimize the amount of packaging in a product, let's say. Well, when I look at this picture, I can see right down here something's going on. This looks to be a minimum. Now as we get further into calculus, we'll use calculus to find this value, but now we're going to look at this graphically and algebraically to come up with it. So I'm trying to come down here and I'm trying to say, okay, what is the value that I plug in here to get this minimum surface area? So this y value is going to give me the minimum surface area. I want to figure out what this is. So each of these tick marks is represented by the unit 1. These tick marks are represented by tens, if you remember my scale. So if I look at this, this looks like 1, 2, 3, 4, 5, 6. It looks like it's between 5 and 6. And we're working with feet here, so it's between 5 and 6 feet. Well, I need an exact value. Between 5 and 6 isn't really going to work. So let's go ahead and jump back to our calculators to help us out. One thing I could do is I could use our table. So let's look at our table. This is the table of values from that graph that we just looked at. Now if we look at these, you can notice that these are big numbers and they get smaller. They come clear down to 105 and then to 103, and then they start climbing up again. So it looks like to me it minimizes somewhere between 5 and 6 and then starts back up again. So that's useful. That kind of verifies what we had from our graph, but we want to find the exact value. So the way we can do that is to go to second calc, and we want to find the minimum value. So we're going to choose that third function, minimum. And what it's saying is left bound. And if you want to, you can arrow over till you're somewhere to the left of the minimum, or I know somewhere to the left is the number 5. I just saw it on my table. So I could hit left is the number 5. My right bound is the number 6. I know it's somewhere in between there. Hit enter to guess, and this comes up with our minimum value. And it is. It's 5.867. So it is between 5 and 6, just like I thought it would be. And that graph again helps us look at that without having to use any calculus. Now when we get to the calculus part of it, it's pretty cool how it works. We'll be talking about derivatives to find this number. But right now we just have algebra to do this. Now another way we could do this is we could work with the function, but again graphing is kind of the faster way to go here. So this point that they're showing us here is the point, and let's just go ahead and round this to 2 places, 5.87, and then the y value is 103.28. So what we have here is a base of 5.87 feet will minimize the surface area to 103.28 feet, square feet, because it's area. So this is the number we're looking for. This is our value of x. What value of x will minimize that surface area? So again, it's a good question. You know, if you're thinking about ideas of business, this minimizes costs in terms of packaging. And if you're thinking about environmental issues, this minimizes the packaging in terms of environmental impact and waste. Now the last example we're going to look at is the quadratic function. And this graph that we're looking at right here almost looks like a bit of a quadratic, but if you notice there's a slant to it. The first part of this, the x squared, would be representative of a quadratic function, but that gets ruined with the x in the denominator. So this really isn't a quadratic function. The x squared portion, if I just considered that, it would be, but it does look similar to a quadratic, which basically is the shape of a parabola. The example that we're going to do next with the quadratic function is to be able to find the vertex of a quadratic function. So a quadratic function, and this is always a bit of a mystery, quad means 4, so you'd think, okay, it has something to do with 4, but a quadratic function has the general form, and I'm going to use f of x notation here, ax squared plus bx plus c. That's the general form of a quadratic function. Now, in order to force this to be quadratic, that leading coefficient a cannot be equal to 0. If that was equal to 0, it would drop it to a linear function. Now back to why this is called a quadratic when you only have the highest power of 2 and you only see 3 terms here. Well, quadratic is the root word, it's Latin for quadratum, which means to square something. So that's the mystery solved. Now if I were to graph a quadratic function, it's going to take on one of a couple different shapes. It could be a parabola opening up, and of course this could be moved around in all different directions. This could be a quadratic formula opening up where it has no points where it crosses. It could be opening up where it has 2 points that cross. So I have 2 solutions. Or it could be a quadratic formula that touches and turns once. So I have 1 solution. So this is an example of no solutions. 2 solutions. Whoops, I guess I don't have to write the number twice. And 1 solution. Now I could also draw the same shapes opening upside down. Okay, so a parabola doesn't always have to open up, of course. So I could have the same thing happening over here, opening upside down, crossing twice, touching and turning once, and having 1 solution. So those could also work with those particular cases. Well, each of these has a particular characteristic, and that's called the vertex. So no matter how many solutions I have, I still have exactly 1 vertex for a quadratic equation. So I would like to be able to come up with this value of this vertex in general. Well, we just did a problem where we looked at graphing these and then going to that minimum value and saying, well, what's going on to the left, what's going on to the right, find the lowest point. That gave us the vertex. Now the vertex could also be at the top instead of the bottom if we have the case where it's opening down. So how would we come up with this vertex? Well, we're going to come up with the vertex by completing the square. Now the equation that represents this parabola is given by this ax squared plus bx plus c. But I can also put this in another form. So we like this form as well. Now we like this form because right away this tells me that my vertex is the ordered pair hk. So if I can get my function ax squared plus bx plus c in this form, it automatically gives me the coordinates for the vertex. So that's what we want to do, is we want to turn this into that. And we do this by completing the square. So let's start with our ax squared plus bx plus c. And again, I'm trying to move this toward a x minus h quantity squared plus k in order to find my vertex. Well, we're not going to worry about having 2 sides of an equation or anything here. We just want to go ahead and focus on the idea of completing the square on one side. So to complete the square, I go ahead and factor out an a. Now this is the tricky little bit here to get going. There's no a here. If I factor an a out, then it doesn't really make sense. Well, let's go ahead and put an a in. If I multiply by an a out front, if you could see it, let me choose a different color. If I multiply by an a out front, I could also divide by an a. And then we can see if I factor an a out, I'm left with b over a times x. Okay? Now the reason I want this c out to the side and not included in this is it's just a constant. The only thing that I have in here are the variables. Now when I complete the square, again I'm going to have this a out front, I want to leave room here for adding another piece. So this is going to be b over a x plus some blank, and then whatever I add, I have to add something else over here. It's not going to be the same value, but I have to multiply by the a. So the way we complete the square is I take half of the linear term. So I take half of b over a, which is b over 2a. And then I square that value, and that's b squared over 4a squared. So the way that this is going to look then, I'm just dragging this down from here, a x squared plus b over ax plus b squared over 4a squared. Now, like I said, we have to add something over here as well. Well, what I'm adding over here is not just the b squared over 4a squared. I have to include the a that's out front that it's being multiplied by. So as I keep working here, I have a, and I want to rewrite this as a product, because again, it's called completing the square, so I want to make this a perfect square. And then over here, oh, I have a bit of a mistake here. I'm adding, but I should be subtracting. So let's fix that up. Now the reason I have to be subtracting is they're on the same side of the equation. So if I add 4, I have to subtract 4 to keep the balance because it's on the same side. If it was on different sides of the equal sign, I'd add 4 to both sides. But again, I have to subtract some value. So I have to make sure this is a subtraction sign. So I'll add c minus, the a's cancel, and I'm left with b squared over 4a. So this is almost in that form that I'm trying to get it to. Now what ends up happening here, I know that x's have to go in each of my front positions, thinking about reverse FOIL. This b over 2a, this value right before I square it is what goes here. And they're both positive in this case because I have a plus for my linear term. If this was a minus, both of these would be a negative. So if you FOIL this out, you will get exactly what we started with right here. So rewriting this, I have a x plus b over 2a quantity squared plus c minus b squared over 4a. So this kind of fits that general form. Remember, the general form was a x minus h quantity squared plus k. So what ends up happening here, the h is the opposite of what it's over here. So my h is equal to minus b over 2a. And then my k is everything that's left over here. C minus b squared over 4a. Now usually you just remember this first one, minus b over 2a. And then once you find your h or your x value, you plug it in to find your y value. So my vertex is given by the ordered pair minus b over 2a and c minus b squared over 4a. So this is completing the square to go through and to be able to find this vertex is a big idea. It's an important idea, and running through the algebra here is good practice at reviewing your algebra. Now you can also use the same idea of completing the square to derive the quadratic equation. And I'm going to leave the specific steps up to you, but I'll get you started on it. So to derive the quadratic equation, we start with ax squared plus bx plus c equals 0. We're trying to figure out what values of x make this equation equal to 0. So that's kind of our rundown here. So you're going to complete the square, just like we did above. The difference will be that above I did not have two sides of an equation I was working with. I just had the one. So here I'll subtract the c, and then I'll add to both sides instead of doing the addition and subtraction on the same side. And after I work through this, I get the quadratic equation, x equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and again, you're going to run through this process by completing the square to come up with this quadratic equation. Now this is one that we usually have memorized and that we can usually go to solve any quadratic equation. Now what we have here then is talking about the number of solutions. So if we were talking about, and again I'm going to use parabolas that open up, but that doesn't always have to be the case. If I have parabolas that never cross twice, or cross once, that's another way of describing the solution. So this was 2 solutions, this was 1 solution, this was no solution. So here we're never getting a value of x that gets this to equal to 0. Now, what would happen in that case with the quadratic equation? Well, what that would end up looking like is this b squared minus 4ac has a direct connection to these types of roots. Now this b squared minus 4ac is something that we just take a quick look at oftentimes to see what's going on with our equation. This is called a discriminant. So what we do then is we analyze this discriminant, and that process is called discriminant analysis. So in this case on the far left, this discriminant, because I'm not getting any solutions at all, is negative. So it's less than 0. So I get complex numbers here. In this particular case, b squared minus 4ac would be some positive number. And in this case, when it equals 0, I only get one root because I'd only be left with this fraction out front then of minus b over 2a for my solution. Here, when it's greater than 0, I can take the square root of a positive number and I get negative b plus that positive number, negative b minus that positive number, the square root. And then here, this is a complex number, so I don't have any solutions. So again, run through that process of completing the square and see if you can work from this point to solve for the quadratic equation or to derive the quadratic equation. Good luck with this assignment. As usual, if you have questions, please feel free to contact me via our chat application on your phone with texting, or you can send me a screenshot or an email as well. Good luck.